Welcome to a new video, Causal Inference, a comprehensive guide. Let's get started. So let's start with the definition. CI, or Causal Inference, is a field that focuses on understanding cause and effect relationships rather than mere correlations. It uses statistical and computational methods to identify, estimate, and validate how one factor is actually influences another factor or can attribute to the target response. CI often intersects with areas such as time series forecasting, econometrics, machine learning, and it helps to give answers to questions like what if, why, rather than just predicting intuition-based figures. When dealing with data that's well structured and labeled, we find that the methods of the CI is actually straightforward, making it possible to uncover clear causal links. And when it comes to data, when it's limited, that meaning doesn't capture all patterns, causal inference can show that too. And I like this description when it reflects on beer. So beer, the liquid, reflect the statistical realistic AI models. And the foam, it represents the unrealistic expectations that usually goes away. So you find that the AI model is degrading over time. Advanced costly analysis that doesn't meet users' needs or expectations. Fascinating use cases in causal inference highlighted in recommendation systems, e-commerce websites, when predicting a predictive machine learning recommender systems that suggest products to users and combine it with causal inference methods to discover users' true intuitions, preferences, and the causes behind their purchase history. Causal methods weigh the average treatment effect. It's one metric popular in CI, and this metric helps us to measure the recommender's causal impact, the effect of recommending an item to user, and when the user is actually converted, and vice versa, when not recommending specific product and the user didn't convert. So the ATE and the causal impact helps with the recommendations, and it helps also so it really beneficial rather than relying only on observational purchase correlations. Another good example here is the pricing strategies. So CI moves from intuition-driven based on historical data, logs, to evidence-based decision-making by capturing the cause and effect relationship and try to detect confounding impact. We will cover the last part later in the next slides. The third practical use case, we see it in medicine experiments. It sheds light on the true cause-effect rather than mere correlationships, aka the association. Association, intervention, counterfacts all merged into the ladder of causation. We will cover this part too in the next slides. And finally, the most fascinating use case when it comes to stocks market. So CI helps investors go beyond raw correlation by examining how a company's financial figures, sector position, and competitive dynamics truly cause movements in performance. CI also focus on identifying long-term potential, helping investors spot hidden gems rather than relying only on surface level, such as ROI metric. Confounding. When we talk about confounding, we talk about external variables that don't exist yet in your model, but still it influences it. This is a most common example when we talk about causal inference. So we have the ice cream and we have the number of peach accidents. If we try to figure out what the cause behind the increased number of peach accidents, your model will probably, or the usual typical data will reflect that it's ice cream. Increase in the sales of ice cream can increase the number of peach accidents, which is not correct because this is not a realistic expectation or a cause effect. Later, when you dig deeper below the surface, you find that it happens in the summer when a lot of people go to the beach. They have a higher chance that will be peach accidents. So this is temperature reflect the confounding variable, the variable that we didn't discover it yet in your model. So external variables that are not included in your model but still influence both the predictor and the outcome, creating a misleading or biased relationship. The problem with confounding is it can't be measured with pure statistics and tests. Instead, we run randomized experiments hoping that can help us grasp all the influential factors that directly influence our predictors. Maybe the ladder of causation, as we will discuss it shortly, can help to make you grasp this bold problem with confounding. We have, why do we need to use CI? So to set the record right, CI pivot on the idea of what factors x1, x2, etc. impact on the target response. Y represents the target response and propose questions like, can we isolate the effect of these factors from other external influences? Can we reliably measure their causal impact? What are the external or confounding factors that might bias the relationship or impact our dataset, limit our understanding of the dataset? And does the relationship involve directional acyclic events, cause effect, rather than correlation? Most common practice is A/B testing by formulating null hypothesis and alternative hypothesis. And still another valid practice is using randomized controlled trials, RCTs for short. This one, the RCT, helps to avoid confounding. Then we have, if the focus is purely on predictive modeling, then we can go with traditional machine learning models like regression, classification, and their methods. And it will be more than sufficient. However, if we want to dig deeper and understand the explanation, interpretation of our model, then we need to intertwine the machine learning model with CI. And now with the ladder of causation. So it basically constructing a clear link between the causes and effects when we train the AI models, so it becomes more crucial for current businesses. CI structure a threshold that helps with AI and machine learning models. Typically, these models are divided into white boxes algorithms and black boxes algorithms. Black boxes algorithms such as XG post or cat post. White boxes can be linear regression because we can interpret the results of the linear regression model, regardless of the algorithms used. CI focus on 3 distinct degrees of cognitive ability: seeing, observing, and imagining. So the ladder of causation help us to understand both the direct and indirect variables that influences a target variable. For an example, let's take a salary analysis scenario. I like this example very much and I have mentioned it multiple times in my other videos. Suppose we want to predict the salary of data analysts in Europe, across Europe countries. Here, salary represents the target response, while factors such as years of experience, education, city, age, the company size are influential predictors. Some of these have a clear, strong, direct effect on salary, our target response. However, others may act as confounders variable that not fully captured by our machine learning model, but still it shape the outcome. This is where causal inference comes in. It helps us distinguish correlation from causation, isolate the confounding effects, and better understand the true drivers of salary. The end result is a model that isn't just predictive but also realistic and impactful. The first degree is association, number one. It's about seeing, understanding, and we can interpret it as naive Bayes method or a simple statistics. It uses the historical data to fathom regular data patterns. It figures out the relation between data variables x1, x2, x3, etc., and the target response. Next, we have intervention. Intervention can be reflected by predictions and experiments, such as A/B testing. So it basically changes one variable to check how it influences the sequence of other variables in predicting the target response. You start communicating with the dataset and interpret its results. And stage number 3, counterfactuals. This is a futuristic phase. What would have happened if we had something differently? What if we omitted X variable? Will that hold a drastic impact on the final results? I like to visualize the ladder of causation into the dark series. I found it's fascinating and quite relevant. So this scene with Jonas watching Hannah and Mikkel knows each other. This is association. It happens in the past. It's related to historical events. Next, we have the intervention phase. So Ulrich looks Hulk to block Mikkel's kidnapping. So this moment of the dark TV show is related to intervention because you are actually interpret and intervene in the events, in the data, in the model itself. And counterfactuals. I haven't seen season 2 or 3 yet, but I can give you a hint. It's about if a character had done XYZ event differently, what would happen to the time loop in the dark TV show? So you can drop a comment and tell me, do you know it? And that's it for today. I hope you enjoyed the comprehensive guide with causal inference. And if you find my content useful, like this video. Thank you, and I'll meet you in another video. Bye.